Good evening. Our main theme tonight is dark matter with Professor Frenk. Before that, one or two news notes. Of course, our thoughts are still very much with the families of the 7 astronauts who died in the Columbia disaster. We still don't know exactly why it happened, but I'm afraid there's nothing to be done now. We only hope it won't happen again. On a more cheerful note, there's been a long discussion about the polar caps of Mars. Are they water ice or are they solid carbon dioxide, dry ice? Well, thanks to the Odyssey probe, we now know they are almost entirely water ice with only a thin coating of dry ice, and that makes Mars look a very much more attractive place. Also, news from the asteroids. Most of the asteroids, or minor planets, move beyond the path of the Earth. Some come inside. Now, for the first time, we found one tiny asteroid, only about a mile across, whose path lies entirely inside that of the Earth, so it's never as far away from the Sun as we are. I'm glad to say it won't collide with us. It never comes about less than a few million miles. Nevertheless, it is the first of an entirely new class of asteroids, and these tiny worlds are always giving us surprises. And now on to our photographic competition. There was some very, very good entries, and Steve Wainwright, John Fletcher, and myself had a very tough time selecting winners. We finally picked out 10 finalists and made a little film of it, and here's how we did it. Well, Steve, John, we've now selected our top 10. Entries all over the world, very high standard. Difficult to choose the winners, but we've done it, so let's now go for our top 10. Now, this one, first of all, Comet Ikea Zhang, photographed by...
No, this is photographed by David Stewart, and this beautiful structure in the tail of the comet there.
Yes, and you can see the gas and the dust stretching out across this wide field photograph, and the stars are pinpoint images. They are absolutely superb.
A nice comet. If you missed it, we'll be back in about 300 years.
Yes.
Right, what are we getting here?
Well, the next one is a picture by Derek Farley.
That's a beauty.
This is beautiful. This is a picture of Messier 74, a face-on spiral galaxy in Pisces. It's absolutely superb.
A really beautiful picture of a spiral galaxy. When you think of only a few years ago, that couldn't have been taken with anything less than a major observatory.
No,
The next one is a picture by E.C. Rodway, and it's very nice, a picture of the Flame Nebula and the Horsehead Nebula in Orion.
And you could also see NGC 2024, the red nebula, like a big flame. It's beautiful with the dark dust lanes.
Now there's a picture of the moon. This is taken by Jonathan Silverlight.
Nice, a nice picture too. The crater Shikar there at the top left, and the Mare Humorum there with the crater Gassendi. Nice definition, and part of the Tycho ray system coming up from the bottom there.
That's right. I agree with you, Patrick. A wonderful photograph
Nice
of the moon.
Nice picture.
And here now is a picture in Hadron Alpha light. This is taken by Kevin Smith, and it's a picture of the surface of the sun.
Yes, it's fantastic. Lots of filaments, dark sunspot areas. Beautiful, beautiful structure.
Right. The Aurora Futura, the Pipe Nebula, and the bright star to the right is Antares. Who took this one?
That's right. This is a picture by Mike Cook, and yes, you can see the dark nebula looking like smoke coming out of a pipe.
A very, very good picture of that.
Nice.
Next. Oh, the old friend of the Pleiades.
Yes, that's right. Now this is Mike Dixon's photograph, and you can see the blue reflection nebulae there.
I like this one.
Yes.
Jupiter being near occultation by the moon. You see the belt of Jupiter, and you see the Galilean satellites too.
That's right. And this is a picture by Mike Tyrrell. It's not an absolutely perfect focus, but it's a real close-up on the planet. And it's a beautiful photograph, isn't it?
It is indeed.
Yes, I agree with you.
Yeah.
The Sculptor Galaxy.
Yeah, this is a beautiful galaxy, one of my favourites. Caldwell number 65, I might add, a beautiful galaxy in sculpture showing its dust lanes and beautiful structure.
This one's very nice, isn't it? This is a picture by Tang Siu Kai, and it's from Hong Kong. And one of the things I particularly like about it is that there's one of the Galilean satellites, and I think that's Ganymede, and you can actually see some hint of detail on the surface of the disk of the moon of Jupiter.
Steve Wainwright, John Fletcher, and myself had a very tough time selecting the winners. Well, we put them on the website, and by a thoroughly democratic vote, the winner is E.C. Rodway with his lovely photograph of the Orion Nebula with the horse's head. So congratulations to E.C. Rodway, and of course to all the others who sent in these pictures. And now to our main theme of dark matter, and we are delighted to welcome Professor Frenk of the University of Durham. Welcome to the Sky at Night.
It's a pleasure.
Dark matter, have we any idea what it is? How do we know it's there?
Well, we don't really know exactly what the dark matter is. This is one of the key questions in contemporary science. what exactly is the dark matter. We know it must be there because it leaves an unmistakable sign of its presence. It produces the gravitational force that permeates the universe. So we know it's there, but we do not know exactly what it is.
In effect, it affects the movements of things like stars.
The dark matter provides the lion's share of the gravitational force in the universe. And it is this gravitational force that keeps together galaxies like our own Milky Way or clusters of galaxies.
Like the Coma cluster, for example, made up of a large number of individual galaxies which don't fly apart.
Exactly. And in fact, the Coma cluster is particularly interesting because it was there that the Swiss astronomer Franz Zwicky first inferred the existence of dark matter. Zwicky, who was a very talented astronomer and also has a reputation for having been a very difficult man.
I met him once, believe me, a very peculiar man indeed, but certainly very brilliant.
Very brilliant, and he measured the velocities of galaxies in the Coma cluster and recognized that the galaxies were moving much too fast. They had too much energy, and unless there was a huge amount of dark matter providing a confining gravitational force, the Coma cluster would have just dissolved. The galaxies would have flown apart.
And the others too, these very distant galaxies, the Hydra cluster, for example.
Indeed, we find dark matter is the main constituent of every galaxy cluster in the universe.
How much dark matter do you think there is compared with visible matter?
Well, the bulk of the matter in the universe we now know quite precisely is actually dark matter. 85% of the mass in the universe is dark matter, and the remaining 15% is made up, about 2 or 3% of that is actually stars, like the sun. The rest is primarily gas. So 85% of the matter in the universe is this mysterious, exotic stuff that we call the dark matter.
Something that's not made up of ordinary atoms.
Absolutely. This is one thing. Although we do not know what the dark matter is, we know what it is not. And it is not ordinary matter. That is the matter that makes the stars, planets, and people. We know the dark matter must be something quite distinct. And we know this because the Big Bang theory tells us that dark matter cannot be ordinary matter. It cannot be composed of atoms like the atoms in the periodic table. It must be something else.
You mentioned the Big Bang. We know now how long ago the Big Bang happened. 13.7 thousand billion years. And that's due, isn't it, to the work of the microwave anisotropic probe, MAP, that's been sending back some amazing results.
Absolutely. MAP is a satellite that, in fact, sent or reported its first results only on the 10th of February this year. And these results have caused commotion amongst the scientific community because we, for the first time, were able to measure very, very fundamental properties of our universe with astounding precision. What we see there is, in fact, an image of the universe as it was when it was very young indeed. What we see there is radiation, which is the heat left over from the Big Bang. This radiation was emitted when the universe was a mere 300,000 years old, which is the human equivalent of one day in the life of the young universe. And MAP took a picture of this radiation as it was at the time. Now, the enormous detail that MAP was able to acquire tells us many, many things about the most basic structure and properties of the universe. For example, it tells us how old the universe is, and the way we can infer the age of the universe from these observations is because with the wealth of detail that we have from these measurements, we can reconstruct the rate at which the universe has been expanding, and because we know how big the visible universe is, we can then infer how long ago the Big Bang occurred. This is only one of the many spectacular results that have come out of this fantastically exquisite. I cannot find the adjectives to describe this experiment.
Because one thing does strike me. We can go back to the time of the Big Bang. We know when that happened, but how did the Big Bang happen?
Well, that is, as of now, a question which lies outside the reach of physics. I think we can go back a long way. We can certainly go back to when the universe was 300,000 years old. We can see the universe then. We can actually go back to when the universe was about a second old and perhaps even a fraction of a second. But what happened in the very moment of creation is still shrouded in mystery. We have to leave something for the future generations of physicists to work on.
What about this stranger named 2DF field?
Well, this was an attempt, in fact, to try and measure how much dark matter there is lying in between those galaxy clusters that Zwicky studied, because We know in the galaxy clusters that there is dark matter, but we suspected for a long time that there should be dark matter also outside the clusters. The so-called 2DF is not a very nice name. It stands for 2-degree field galaxy redshift survey, which is the largest survey ever undertaken of galaxies in the universe. It was carried out with a robotic fiber optics instrument called the 2DF instrument at the Anglo-Australian Telescope, and the survey was finished just a few months ago. Now, it tells us a huge amount about the dark matter, and the way it does it is very ingenious. We know that the universe is expanding, the galaxies are all moving away from each other, but it turns out that the expansion is not perfect. The galaxies actually wriggle around as the universe expands under the influence of the gravity produced by lumps of dark matter. With the 2DF survey, we've been able to measure these wriggles and therefore infer how much dark matter there is in between the galaxy clusters. It's a very similar principle to the one that astronomers classically use, for example, to infer the existence of moons or planets that we cannot see. Because even if you don't see a planet, you suspect it's there. You know it's there because it causes wriggles in the orbits of other planets that you can see. It's exactly the same principles, but applied on the scale of the universe as a whole.
I think we've cleared up now one more question. The old question, will the universe expand forever, or will it finally galaxies come together again in a big crunch? I think the big crunch is now probably out.
Exactly. All the present indications are that we live in a universe which not only will continue expanding forever, but it'll do so at an increasingly frenetic pace. The universe we now know, in part from measurements like those of the MAP survey, we now know that the universe expansion is accelerating rather than decelerating, we used to think a few years ago. And this acceleration will continue, and the universe will grow into a vast frozen expanse.
So we're looking right back in time.
Absolutely, and a fascinating aspect of these measurements is that we learn a lot about the dark matter. We learn a lot about how much dark matter there is, and the reason I was so confident that 85% of the mass in the universe is dark matter can be traced back to these tiny little irregularities in the microwave background radiation, because these are precursors of galaxies, but it is the dark matter that controls the growth of galaxies. So by measuring the sizes of these precursors, we can figure out how much dark matter the universe contains. And so this is one of the main lines of evidence for our understanding of dark matter.
It seems so strange. There's something entirely alien, really. There's no chance it could be ordinary matter locked up in black holes, for example, or low-mass stars?
Well, it could be perhaps matter locked up in black holes. We're almost certain that it cannot be mass locked up in stars, because the Big Bang theory tells us that only about 15% of the mass in the universe can be ordinary matter, which is the matter that makes up stars. And so, whereas we know that, of course, there's much more dark matter than is allowed in ordinary matter. So for that reason, we're very confident that it cannot be invisible stars or planets or Jupiters. It must be something much more exotic.
What about neutrinos, these strange, amazingly plentiful particles that have apparently no electric charge and no mass? If they have any mass at all, could that be the answer?
Well, 20 years ago, in fact, when I started in cosmology, the first big project I had was to try and figure out whether the dark matter could actually be neutrinos. And I remember being very depressed when it turned out that it was really very difficult to explain our universe if the dark matter was made up of neutrinos. And the reason for this is that the dark matter controls the evolution of the universe. The dark matter is the regulator of the formation of galaxies and structure, and it turns out that if the dark matter had been made of neutrinos, galaxies like the Milky Way would have never been able to form.
I see.
We need a different kind of particle, not necessarily very dissimilar from a neutrino, in the same category of elementary particles, but we need a different kind of particle, something that physicists call dark matter, which, although similar to the neutrino, it has a different type of property and allows galaxies to grow.
What exactly are the investigations going on? Are they purely theoretical, or do you have special equipment for dealing with it?
Well, for dark matter, interestingly, there is a prospect of building a machine that will detect dark matter. Because if the theory is correct, then there are billions of cold dark matter particles raining onto the Earth every second. This room is full of them. And so, but they're very difficult to detect because they just basically go through everything, and they only interact through gravity. So what is needed is a device which is very, very sensitive, sensitive enough to record a collision between a cold dark matter particle and a single atom in a detector. Now that technology exists, and there are some very exciting experiments on the way. Because lots of other things rain onto the Earth, cosmic rays in particular, it is necessary to shield these experiments, so they take place usually in deep mines or tunnels, and these experiments have now been going on for a long time, and my view on this is that it's a race to discover the dark matter, and the race is probably coming to a close.
I remember going down a Homestake mine in America where they were detecting neutrinos, and of course we have Bulby mine here, haven't we?
Exactly, and the Bulby mine in fact hosts one of the most advanced experiments. It is very harsh conditions in which to do physics. I'm glad that I'm a theoretical cosmologist rather than an experimental physicist, because these people work on very harsh conditions, but the detectors they have and the technology they have deployed a mile on the ground is really very, very impressive.
Well, these investigations are going on, theoretical and shortly or practical. What hopes have you of really finding out what dark matter is in the foreseeable future?
Well, I think my bet is that we will find out what the dark matter is within the next few years, say within 5 years or so. And I base this confidence not only in the sophistication of the experiments, but also in a different kind of experiment that cosmologists can do nowadays. The ultimate experiment we could do in cosmology would be to create a universe. In fact, why not create more than one universe? Why not create many universes with different kinds of dark matter? Of course, we cannot just create universes just like that, but we can actually create very good replicas, virtual replicas, using very large computer simulations. And the modern supercomputers are so powerful that they allow us to recreate the entire cosmic history. Now, we can make virtual universes, put different kinds of dark matter in it, and see what comes out, and see which of those looks like the real one. Now, it turns out that only universes which have dark matter of the right sort produce universes that look like our own. And so this indirect evidence suggests that we're getting very close to the solution of the dark matter problem.
That, of course, is why we're here in the universe. If you do solve it, please come back to the sky at night and tell us just what you found.
It would be a pleasure.
Carlos, thank you so much.
Thank you very much, Patrick.
Don't forget, you can still enter our competition for drawing a Martian base, so please let us have your interest. Don't forget our website, www.bbc.co.uk/space, or CFAX, page 620. Now, this is very much the year of Mars. Mars is becoming very bright in the sky now, and all kinds of probes are going there. Are we going to find life there, or have we done so? In our next programme, I'll be joined by Professor Colin Pillinger, who is the designer of the British probe Beagle, which will land on Mars before the end of the year. So join us then to have the latest news from the Red Planet. Until then, good night.